In this video, we're going to look at magnetism and anomalous configurations. Magnetism is based on unpaired electron orbitals. If we take a look at iron, iron has the following electron configuration. So it has the inner shell of argon, followed by 4s2, 3d6. So it has 2 electrons here, and then 1, 1, 1, 1. So it has 1 paired electron and 4 unpaired electrons. So how does this relate to magnetism? Well, these electrons, all with the same spin, produce a magnetic field in the same direction, and they basically act. This atom acts like a tiny magnet. This atom can then influence other atoms next to it and therefore align its magnetic poles in similar directions. In iron and other metals like cobalt and nickel, you can have what's called domains. And a domain is a group of atoms that are influencing each other and have the same magnetic direction, right? Now, in an unmagnetized substance, all these domains are pointing in different directions. But if exposed to an external magnetic field, then all the atoms can be influenced to point in the same direction, and then you have, for example, all of them pointing in this direction. So this is magnetic north, and this is magnetic south, and you have some magnetic material. Again, on the subatomic level, it's the fact that these are unpaired magnetic spins that allow the atom to have a singular magnetic moment or a singular magnetic direction. Once the electrons are paired, then those magnetic properties are canceled out. So you can see iron has many unpaired electrons and therefore has a strong magnetic property. Same thing with cobalt. Cobalt is also this as well. It's 4s2. In this case, it's going to be 3d7. So it has 2 orbitals with paired electrons and then 3 unpaired electrons. So 2 paired and 3 unpaired, nickel being this argon. 4s2, 3d8. These 3 elements are known as the ferromagnetic elements. These elements are the only ones where their solid structure allows them to produce domains. These are the 3 elements that can produce domains. There's another element as well, but we're not going to get into it. So ferromagnetism is caused by unpaired electron spins. It exists in iron, nickel, and cobalt because the atoms are small enough and positioned to influence each other and produce domains. When domains align, a permanent magnet is produced, and these substances are strongly attracted to a magnetic field. Paramagnetism is also caused by unpaired electron spins. However, no domains form in these substances, which means we cannot have permanent magnetic properties. It is weakly attracted to a magnetic field. Now, when a substance has all paired electrons, we call that substance diamagnetic. And examples of families include the noble gases and the alkaline earth metals, they are weakly repelled by a magnetic field. Anomalous configurations. Most elements experimentally agree with the predictions of our theories. However, there are two major exceptions to be aware of. The main exception, or the main explanation, is that half-filled and filled subshells are more stable and have lower energy than unfilled shells. So that's what we're reading right here. This is more important for d orbitals than it is for s orbitals. The term electron promotion is important as it plays a role in chemical bonding as well. So again, the idea here is half-filled and filled subshells seem to be more stable than unfilled shells. And it's more important for D than it is for S. So if we look at copper, okay, this is going to be a condensed energy level diagram. We'll call this a condensed energy level diagram. So copper has the inner electrons of argon, and then it has 4s with 2 electrons, 3d, 5 orbitals there, and then this electron configuration. Now, this is what is predicted based off of Aufbau, so based off of going from lowest energy to highest energy. But what we see again is that half-filled and fully filled subshells are more stable than unfilled shells, and it's more important for D than it is for S. So what ends up happening here is that this electron gets moved from the s orbital up to the d, because as we can see, it's more important for D than it is for S. And this process is called electron promotion. We call it promotion because it's moving from a low energy to a higher energy subshell. And so what we see in reality is that copper actually has this electron configuration. It's got a half-filled S subshell, and then the D is fully filled. We can see this with chromium as well. Chromium has an inner set of electrons that's isoelectronic with argon, and then it has 4s, 2 electrons here, 3d, but in the 3d shell, instead of being paired, we have these single electrons in an upspin position. Again, we go back to this rule, which is half-filled, and filled subshells are more stable than unfilled shells. It's more important for D than it is for S, so electron promotion is going to happen here. So an electron from the 4s gets promoted to the 3d subshell. And what we see actually happens is we have argon here, 4s with 1 electron, and then 3d. And all with an upspin, and so this is half filled, and it tends to be more stable. Finally, there are some challenges to the quantum mechanical model, and they're listed here below.